So let's solve some examples on topic 3.2. He's saying, under what condition of pressure and temperature does a real gas approximate to an ideal gas? If you remember, we said that it needs to be a low pressure, high temperature, low density. Okay, the STP conditions: 1 atmosphere, which is low pressure; high temperature, which is the 0 degrees Celsius, which is the 273 Kelvin, and low density as well. So C is going to be the answer. So here, in another way, under which condition of pressure and density a real gas is approximated as an ideal gas? We just mentioned this, so it needs, of course, the pressure needs to be low and the density needs to be high because the volume is going to be high in this case. So if you notice the PV equal nRT, for a low pressure, high temperature, the volume is going to be high, which means that the density is going to be low. I made a mistake here. It should be D. So let's do it again. So here we said the volume is going to be high because this is high and this is low, which means that the density, which is the mass per unit volume, is going to be low as well. Okay, so it's going to be D. A fixed mass of an ideal gas is trapped in a cylinder of constant volume. Okay, so this is the isochoric process. And its temperature is varied. Which graph show the variation of the pressure of the gas with the temperature, but the temperature is in degrees Celsius? So let's get back to the constant volume. If you remember, look at the graph. In degrees Celsius, it's shifted back. So it's this graph. So if I would like to choose one of these, of course, it's not this, because if you remember, it was P over T equal NR over V, which is constant. So in this case, it's going to be P equal NR over V times T. So if this is on the Y and this is the T is on the X, then this is the slope. So it's going to be a straight line. So I'm going to remove these two because it's a straight line that passes through the origin unless the temperature is in degrees Celsius. So if it's in degrees Celsius, if I'm going to elongate this part, so yes, it's going to hit the temperature axis on minus 273. So this is the answer. So it doesn't pass through the origin. If he said in Kelvin, then yes, this will be the answer. But he said in Celsius. A sealed cylinder of length L and cross-sectional area A contain N molecules of an ideal gas at Kelvin temperature. What is the force acting on the area of the cylinder marked A due to the gas? So we know that it's an ideal gas. So PV equal, he want in terms of N, okay? So I need to use the other equation in terms of the Boltzmann constant, which means that I can find the force from here. The force per unit area times the volume is equal to N kBT. The volume can cancel out because the volume is area times the length. So if you want, I can write it like this. It's area times length. So this is the volume over area equal to N kBT. The area is going to cancel out and the force is N kBT over L. So it's going to be D. An ideal gas has a volume of, a temperature of, and a pressure of. The volume of the gas is reduced to, so this is the V2, and the temperature is raised by this much. Okay, so it's raised to, so this is the T2, and he's asking for P2. So this is the V1, T1, P1. So I need to use the general gas law here, okay, which states that P1 V1 over T1 is equal to P2 V2 over T2. Now I would like to say something here. No need to convert from kilopascal to Pascal, because usually the conversion is times 10 to the power of 3, so it's going to cancel out from both sides. Moreover, No need to convert from milliliter to a meter cube, because also it's the conversion is going to cancel out in any ways because it's a multiplication. But for the temperature, you need to convert to Kelvin because you're adding 273 each time. So P1 is 100, V1 is 15, and T1 is 20 plus 273. P2, I need to find it. V2 is 5, and T2 is 40 plus 273. So what can I do here is that I can remove the 5 with the 15. I will end up having 100 times 3 over 293 equal to P2 over 313. So in this case, P2 is going to be equal to 300, but this 300, I need to multiply it by 313 over 293. So as you can see, of course, I can't use a calculator, but the answer should be close to 300. Okay, why is this? Because this is a bit more than 1, this ratio. So the answer is going to be B in this case. Okay, of course, it's in kilopascal because I did not convert. It's still in kilopascal here. So it was 100 kilopascal here. Now let's solve some paper 2 question. He's saying that the air in a kitchen has a pressure off and a temperature off. The refrigerator of internal volume, of course the volume of the fridge is not going to change, so this is constant, is installed in the kitchen. The refrigerator door is closed. The air in the fridge is cooled up to this temperature, and the number of molecules in the fridge stays the same. Okay, so that's true because you're opening and closing, so the number is going to remain the same as well. With the door open, the air in the refrigerator is initially at the same temperature and pressure as the kitchen. So the T is going to be 22 degrees Celsius, and the pressure is going to be 1 atmosphere, which is power 5 Pascal. Calculate the number of molecules of air in the fridge. So to solve part A, I can use the PV equal nRT, of course, but I'm not going to use the nRT because he wants N, so NKBT. And what can you do here is you can rearrange this equation in such a way that you make N as the subject of this equation. And all what you have to do is to just substitute. So P is 1, V is 0.36 meter cubed over KB. I need to find it from the data booklet. Just 1 second. Let me bring it from the data booklet. Okay, so KB, the Boltzmann constant, it's 1.38 times 10 to the power of minus 23 times the temperature. It needs to be in Kelvin, so it's 22 plus 273, and the answer is going to be 295. And you just plug this into your calculator. Let me do it quickly. But you have to be careful while using your calculator. Divided by 10 to the power of minus 23, and the answer is 1.54 times 10 to the power of 21. So this is the number of, he said, molecules of air in the fridge. So let me repeat it quickly. I guess I missed something here. So it's 10 to the power of 5 Pascal times 0.36 divided by 1.38 divided by 10 to the power of minus 23 divided by 295. Okay, so that's why. So here the answer is going to vary. So it's going to be 8.84 times 10 to the power of 24 molecules. And then you continue. Next question. So here he's saying that in part BI, he's saying determine the pressure of air inside the refrigerator. So in this case, if this is the number of molecules, okay, so this is the number of molecules, and we know that the volume is going to remain constant, and this is the temperature inside the fridge when it's closed, then in this case I can find the pressure. So I can use it by using P equal NKBT over V. Also, what you can do is that you can also use this because it's a constant volume, so you can use P1 over T1 is equal to P2 over V over T2 because NKB over V is constant, so the ratio of P over T is always constant. So I can also use this. So let me use this. So let me use this one. So I can write that P2, which is the pressure inside the fridge, is equal to the pressure outside over the temperature outside, which is 295, times the temperature inside, which is 5 plus 273, which is a 278. In this case, if I do it, the answer is going to be 94237, or 9.4 times 10 to the power of 4 Pascal. So this is the pressure inside, and this is the pressure outside. So that's why the fridge is closed, because if the pressure inside is more than the pressure outside, then the fridge will be opened. Okay, so anyway, let's look what he's going to ask. BII, the door of the fridge has an area of, so given the area of the fridge, show that the minimum force needed. So here he's asking for the minimum force needed to open the door is this much. So let me do it on another page. But let me bring, I need this, the pressure which is inside, I need it. And I need the area, which is 0.72. So he said that the area is 0.72 meters squared. And he said that the atmospheric pressure, which is outside, is, so this is the P in, this is the P out. And he's asking for the force in order to open the fridge. So basically we know that the pressure is the force over area, which means that the force is the pressure times the area. But this pressure, what you need to know is that if this is the fridge, there's a pressure from inside and there's a pressure from outside. So in order to know how much should I be pulling, with which force I should be pulling the door of the fridge, I need to know what's the difference between these two pressures. So basically, this is the change in pressure, or the difference basically in the pressure. So F is the P out minus the P in, the outward pressure minus the P in, times the area, which is 1 times 10 to the power of 5 minus 9.4 times 10 to the power of 4 times the area, which is 0.72. And the answer is going to be so the answer is 4149.2 Newton. Let me check. He said, let's prove it that it's 4 kilonewton, is it? Yes, it is. So it's approximately 4 kilonewton. Then he said, comment on the magnitude of the force. So if you look at the magnitude here, it's a very huge magnitude. Okay, so the first comment that I need to say, this is part II. So this was BII, this was BII. Now I need to comment in BIII. So the comment on this is that the force is huge, which means that the method that we were using is wrong. And why it's wrong? Because we considered the gas as an ideal, and maybe it's not. Maybe it's a real gas. So maybe it's a wrong approach used. Okay. So that's it. We solved some paper 1 questions and some paper 2 questions. Of course, you can solve more on the IB question bank, but this is fine. Okay, so that's it for today.